Hello everyone, welcome back. Previously, we considered the DC analysis of a full common emitter amplifier, where voltages were measured across the various test points of the amplifier. If you haven't seen that video yet, I encourage you to click on the link below to see it. My name is James Apanda, your private tutor for understanding electricity. In today's video, we are going to consider the AC analysis of the same amplifier. As you can see back there, I have already fired it up. So without wasting my time, let's go back there and see what is happening. Okay, so here we are. I believe that you are familiar with this circuit. This is what we tested in the previous video, and we said that the DC values are indication that the amplifier would properly work. The only changes I have made so far is to include these two capacitors. Now these are coupling capacitors which will allow AC signals to flow and block DC signals at the same time. Now the reason why we are bringing this coupling capacitors is that we are going to look at the AC analysis, where we'll be feeding an AC signal, or let's say a sinusoidal signal, from the function generator here. This is a function generator. So we'll be feeding a sine wave into the amplifier, and we don't want the DC voltage that is used to power the transistor amplifier up to interfere with the AC signal. So that is the reason why we have the capacitors installed. So we also have the function, the oscilloscope here is a 2-channel oscilloscope. So this is for channel 1 and this is for channel 2. And when you come here, you realize that channel 1 has an input and channel 2 also has an input. Yes. So if we want to feed a signal into channel 1, we feed it to the input through these alligator clips. The same applies to channel 2. So this for channel 1 and this is for channel 2. So quickly, let's feed the signal into both channel 1 and 2 in turn and see how the signal looks like. So first of all, we connect the negatives and then the positives. At the moment, it's not showing any signal because the amplitude is down. The amplitude is down. So I need to increase the amplitude. Up, 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 and up. So as I increase the amplitude, as I vary the amplitude knob, the waveform is also varying. All right, so let's look at that of channel 2. So we only need to disconnect this and then bring channel 2's alligator clips on board. So we connect the black to black and then red to red. So once again, we have to vary the amplitude knob to increase and decrease the waveform on channel 2. Okay, so now that we know that a signal that we are going to feed into the amplifier is a sinusoidal wave, let us quickly fire the amplifier up with the battery as well as the AC signal. So let's power up the amplifier. Let's connect this to ground and connect. This is the input side of the amplifier. So this capacitor C1, and then we connect channel 1 to the same input, because we want to monitor the input signal on channel 1. So we need to connect the channel 1's alligator clip to the input so that we can monitor the input signal on channel 1 of the oscilloscope. So currently there is no output showing in channel 2 because we've not connected the output of the amplifier yet. Channel 2 is going to be used to monitor the output waveform. So let's quickly do that and see what we have. So this is the input voltage. Let me reduce it a little. So I have reduced it. Let me now connect to the output. Now this is the output. This capacitor is the output coupling capacitor, that is C2. So let's connect it quickly and see. Wow, that is super fantastic. The signal is very large. So let's use this to bring it down a little. Let's reduce the input. This is great. With a very little input voltage, we have a very high output voltage. A very high output voltage, and that is so serious. Yes, so you can see the output voltage is very large, indicated by the blue graph. Let's reduce the input signal a bit so we can have a smooth output voltage waveform. All right, so you realize that with a very little input signal, we have a very large output signal. Now let us change the settings on the oscilloscope to get a much better waveform. So we are going to adjust the voltage per division knob. So we're going to change this from 1 volt to about 200 millivolts. So that is it. That causes the input waveform to increase in magnitude. And then let us also okay, so let's maintain the settings on the on channel 2. So we still maintain 1 volt per division for channel 2, and let's increase the signal again and see. Yeah, so there you go. So for this, you have an input signal, which is, let's take a look at the input signal. Let's try to bring this one down and see the voltage. Okay, so we have 1, 2. So the waveform is covering 2 centimeters, and every centimeter has been set to 200 millivolts. So we have 0.4 volts per the waveform. 0.4 volts per the waveform. So the input voltage waveform here is 0.4 volts. And or if you like, you can say this is 400 millivolts. 400 millivolts or 0.4 volts. And then let's look at the output. The output is so large. so large. Yes, let's see how many divisions the output has covered so far. We have 1, 2, 3, 4, 5, 6, and then 7. Let's see if we can have more. Oh, we can actually have more. Wow. We can have more without any distortion. Okay, so we are not having any distortion because we have a smooth curve at the bottom and top of the waveform, so we don't have any distortion. And let's see the number of divisions or the number of centimeters that the waveform has covered from top to bottom. So we have 1, 2, 3, 4, 5, 6, 7, and 8. 8 multiplied by, that is 8 centimeters multiplied by 1, that is 8 volts. So for an input voltage of 0.4 volts, we are having an output voltage of 8 volts. That is very, very large. And if we want to look at the calculation for comparing the output voltage to the input voltage, then we have the voltage gain, which is equal to V out over V in, and V out is 8 volts and V in is 0.4 volts, and this gives us 8 divided by 4 is 2, so this is 20. If we express this in decibels, then we are going to have 20 log to the base 10, 20 here. So we have 20 log 20. That gives us 26.02 decibels. So that tells you that this amplifier can really perform very well. So yeah, that is these are the test results for the AC analysis, and I believe that you are going to try this and enjoy. Yeah, so another thing that I want you to take notice of is the output voltage, the direction of the output voltage. You realize that when you compare the output voltage waveform to the input voltage waveform, the input rises to the positive and descends to the negative, or falls to the negative, whereas the output rather goes to the negative first. So as the input is rising to the positive, the output is rising to the negative before rising to positive. Now, this tells you that there is a phase shift of 180 degrees. So for the positive half of the input waveform, we have a negative half of the output waveform. And when the input waveform falls to negative, at that same time, we have the output waveform rising to positive. And for this reason, we say that a common emitter amplifier is the output of a common emitter amplifier is always 180 degrees out of phase with the input voltage. So there you have it. I hope you were able to follow through the procedure from start to finish. Kindly let me know in the comment section if you have any questions about what we did back there. Please like and share the video, And if you haven't subscribed to my channel yet, stay connected. Hit the subscribe button and keep the current flowing. See you next time.